before I move forward, your colleague asked me a couple of questions and I want to translate them, okay? Because I think it's useful, and a couple of them, he asked me 3 questions. A couple of them I think they are useful. So first of all, he asked me what's the difference between the observation that we use to calibrate the model and the output from the model. So basically the question is, what's the difference between the observations and the synthetic data? And I think it's important to clarify this point, this issue. So basically you have observations that you use to calibrate your model, and then once the model is ready, you use the model to generate synthetic data. So you may have the doubt, why not using the observed data directly? So this could be your doubt. Why do I need to generate synthetic data? So there is an essential premise that you have observed data, but they are not enough to support your design challenge. Like, I have to design a dam. I have 10 years of data, river flow. They are not enough to design a dam. So you have to extend your information. So the idea is, I use the 10 years of river flow to calibrate a model, and then I use the model to generate the synthetic data. So this is the rationale. And then of course you may wonder whether this procedure allows you to extend the information. Because of course if the model is good, then you extend the information. If the model is wrong, the generated data, synthetic data, are not good to support your design mission. Okay? So this is another question, of course. In any modeling exercise, you have always to wonder whether the model is providing a good interpretation of the process. And here the reply to this question is very diverse. There are situations in which the model works well, other situations in which they don't. So you have to try to understand if this model is providing a good performance. I will give to you some indications to judge the performances of the model. But the rationale is very clear. So you have enough data to calibrate a model, but not enough data to support your design. If you had 1,000 years of data, there is no need to generate synthetic series to design a dam. Okay? But if you have 10 years, then you have to generate the synthetic series. And you may use a Rain-Foronov model or a stochastic process or other methods that we don't deal with. First question. Second question, this is more delicate because he asked me, you mentioned that at each time step you define a random variable and then the stochastic process is the collection of the random variables. But then he told me, he asked me, but when I have my observation, like x1 or q1, don't be concerned by different symbols. Using x or using q is the same. So when you have an observation, this is one number, so why treat it as a random variable? So basically, if I go over the Po River on January 1st, and I measure the river flow, this is one number, so he asked me, why do you need to define a random variable? Okay. Why do I need to define a random variable? Because think of the situation in which you go over the Po River before taking the measurement. If you define a random variable for the river flow on January 1st, you have an idea of what you are likely to get. You know the average, you know the standard deviation, so you can get a guess, like I'm expecting to measure 100 because the mean of the probability distribution is 100. And also, if you know the standard deviation, you may say with a probability of 90%, I can get from 95 to 105. So if you define a random variable, you can get a guess. If you don't know the data, then you go there, you get the data, and then it's no more a random variable, it's your data. But defining a probability distribution allowed you to get a guess in advance. Given that I want to generate 1,000 years of data, and I don't have the data for 1,000 years, then I certainly need to define random variables, because I get my guess. Okay? This is the reply. Don't make confusion between the random variable, which is a probability distribution in which your observation falls, and the data. The data is just an outcome from the probability distribution. And I need to define a stochastic process because I want to generate data for days where I didn't go there to take the observation. If I want to generate 1,000 years of data, 1,000 years ago, nobody went there to take the observation. So I have to define the stochastic process and the random variable. And then I use the observations and I treat them as outcomes of these random variables, from these random variables. The same if you use an A4 model. You don't know the number, and you define the number in some way. You define it using, in the case of the A4 model, a deterministic relationship. In this case, you use a statistical relationship. So you don't define the number, but you define the random variable. It's not easy, but it's important that you get a perception of what the meaning is, because statistics is nothing else than a tool to deal with uncertainty. When you are uncertain of something, then statistics is just a tool to deal with it. Okay, so basically let me go back to stationarity, which is more interesting. So the question is, as I said, should I use the data? Yes. And if you see that something changed, then use it to take your decision. And this is what I always say to climatologists. They say climate is changing, so it's non-stationary. And I always reply by saying, please, if you say that it's non-stationary, you also have to give me information on non-stationarity. Just tell me what is changed and how much, so I can inform my design. Just saying that climate is changing without quantifying the change is useless and leaves to us no other solution than using stationarity, than using past data. And this is the problem with climate change. The climatologists keep saying that climate is changing, but they don't say how much and how it's changing. So it would be very useful if they could say that the return period has to be decreased. The return period may be that you don't know this definition, but if they said that the peak flow is increased 20%, that's fine. But if they just say peak flow is increasing and nothing else, how can we inform our design exercise? By just using the past data. So don't be, how to say, I don't remember if I started here. Yes. Don't be concerned by what you read on the newspapers, that climate is changing, everything is changing, and therefore you can't use the data. My recommendation is use the data. And of course, if you have quantitative information on some changes that occur, just keep it into account. Take it into account. If you don't have any quantitative information, but just suppositions, just ideas, then use past data. This is important. And you know, because when we speak of hydrological design and river flows, design of bridges, dams, climate change comes into play. It's very important, but we have to know that while there are some aspects of climate change that are very clear, like temperature increasing, not everywhere at the same pace. Somewhere the temperature is increasing more than in other places, but this is a fact that is proved and quantified. But for other meteorological and climatic variables, there is no clarity. So it's not clear if, for instance, extreme rainfall in Italy is increasing. Some people keep saying that we have the bombed aqua, it's water bombs today, which means very frequent and very violent storms. There is no evidence, if you look at the data, that the frequency of very intense storms in Italy is increased in the past 50 years. There is no evidence. So just pay attention, because you know this is a problem that is impacting our life of engineers in a very significant way, and to get oriented is not easy. I'm writing now a paper to clarify the concept of stationarity and the use of stationarity in a climate change context, because there is a total confusion. Even on the scientific journals, on climate change, there is a total confusion. Okay, that's it. So stationarity is fine. And you know what it means. And basically what you have to know is, refers to a stochastic process. That means that the probability distribution is not changing in time. That's it. And then there is, on the slides, defined ergodicity with a formal definition. Let's forget it. I just would like to say that ergodicity means that from a limited amount of data, you can estimate the statistic of the process. Like, let's suppose that you have just 1 year of river flows of the Po River. You take the average, and you assume, for 1 year, you assume that this is the average for the Po River, for whatever years, whatever number of years. This is an assumption that allows you to use reduced pieces of data to estimate the statistics. Very dangerous assumption, okay? Because, of course, how long is, for a river, the minimum amount of information that you need to be sure that you got the statistics of the river? If one asks you, how many years of data, daily data, hourly data, do I need to estimate the peak river flow for this river, and brings you over a river, and this client says, can you please tell me how long I have to measure the river flows in order to estimate the peak flow? What would you reply? Very difficult question. Because, you know, the peak flow is something that may occur tomorrow, or may occur in 50 years from now. You didn't understand what I said?
The name.
The name of what?
The beginning of this
Okay, this is ergodicity. Sorry, I didn't write it down. I'm not interested in it. I won't ask you what is ergodicity at the exam. I just want you to know what it means, okay?
Could you repeat
The meaning, yes, it means, in practice, I'm not providing the formal definition. The formal definition is on the slides. My suggestion is forget it. The meaning is that from a limited amount of data, you can estimate the statistics of the process. From a limited amount of data, you can estimate the statistics. I may ask you a question. In your opinion, how many times do you need to toss a coin to guess that the probability of getting a tail is 0.5? So for sure, one time is not enough. Because if you don't know anything of the coin, you toss the coin, you get a net. And your conclusion would be the probability of getting a net is 1. Then, how many times, in your opinion, do you need to toss a coin? So Pearson tossed the coin for, I told you, 24,000 times. And he got very close to 0.5, but not really to 0.5. So it's a good question. And the tossing a coin is easy. I would say that you just need 10, 15, and you get very close. But if you speak about a river, not so easy to estimate. There are a lot of papers on the minimum amount of information that is required for rivers to get a good estimate of extremes. Okay, by the way, ergodicity is this assumption. This is the meaning. Good. Now, how to judge the performances of this model? For sure, you need to check the assumptions. If they are not satisfied, you know that the model is not, strictly speaking, good. And of course, you may say that they are reasonably satisfied. It's your call, because of course X will never be Gaussian, epsilon will never be zero mean. It's your call. Of course, when designing, you can accept some approximation. There is another thing that you may test, which is what is called the explained variance of the model, which is very similar to the R-square index of the regression. But let me call it explained variance. The explained variance is equal to, let me call it sigma SP is equal to 1 minus sigma square epsilon divided sigma square x. And there is a top value for the explained variance. The top value is when the model is perfect. Epsilon is identically 0, so the variance of epsilon is 0, and then the top value for the explained variance is 1. So this is max 1. This is similar to the Nash efficiency, by the way, very similar. And min is minus infinity. Let's say that if, like the Nash efficiency, if the explained variance is 0, then the model is useless. Like for the Nash efficiency, if you get an explained variance of 0.6, 0.7 is fine. It means that the model is quite good. Okay, then on the slides you will find a statistical test for checking Gaussianity. Let's forget it, okay? Because I told you before, it's your call to decide whether the assumptions are satisfactorily met or not. And there are indeed statistical tests that can help you. Let's forget about them because I don't want to focus on too many details. So it is on the slides, but let's forget it. Good. Now, I told you, second part of information, extension of the model. So I am happy with the theoretical basis. I think you have a good basic knowledge of stochastic processes. Let me extend a bit. And extension means, what if the process is non-Gaussian? X is non-Gaussian. What can we do? There is a very simple solution, which is transforming X, preliminary transformation of X to make it Gaussian. Again, very simple and straightforward solution. Preliminary transformation of X to make it Gaussian. For instance, the logarithm. Take the logarithm and you are very likely to get to a Gaussian distribution. So this is closed for me. First extension, non-Gaussianity, preliminary transformation, for instance, the logarithm. There are a lot of transformation proposed by the literature. I'm not going into more details. The logarithm is the one that is more frequently applied. Good. Second problem. Seasonality. This model is not able to reproduce seasonality. What is seasonality? Seasonality means that the statistical behaviors of X are regularly changing along the year. Regularly. What is the problem with seasonality? This model cannot reproduce these regular changes for its structure. It can reproduce variability, but not in a regular way. You need to modify the model. I say again what I just stated. This model can reproduce changes. It's a stationary model, basically. If you take care that phi1 is in absolute value lower than 1, as I said, it's stationary. But still, it can reproduce changes, like a flood. But it can reproduce random changes, not regular changes. So the model, randomly, it decides when the change occurs. You cannot impose regular changes, like seasonality. Seasonality is a regular change. So, one possible solution, I already mentioned it, is to change the model. Too complicated. I don't want to introduce seasonal models. A second possible solution is another preliminary transformation. This is very useful. And this preliminary transformation is called deseasonalization. So you take X, you transform it so that the resulting time series is no more seasonal. Not always this is possible, but in hydrology, yes, I think this is a useful solution. So let me write down this transformation in analytical form. Okay, and okay, before writing it down, let me think about if I have to provide a preliminary definition. Yeah, I think so. Okay, so I first need to provide a preliminary definition. Let's suppose that we deal with daily data, but the method that I am now describing applies to any kind of seasonal data, so it will be also hourly data. It doesn't change. Of course, seasonal data means that the data are observed at a time step that is lower than 1 year. So it could be hourly, daily, or monthly. If you look at annual data, like annual average river flow, this is not seasonal. No more seasonal, because you averaged out seasonality if you look at annual time scale. So let's suppose that we deal with seasonal data, and let's suppose that they are daily data, just to make it simple. But again, this procedure applies to any kind of seasonal data, and I have to now to write down an analytical relationship for computing the seasonal mean. What is the seasonal mean? It means, like if you deal with daily data, the mean of all the data observed on the 1st of January. And then the mean value of all the data observed the 2nd of January. So I need to define the average value and the standard deviation, because I need these two statistics for the data observed in the same day. And in analytical form, one has to think about the symbols to use, no? Okay? Let's suppose that we have capital N years of observations. Or maybe I used capital N to, as a symbol for the number of synthetic data to be generated. So let me change the symbol, not to make confusion. Let's use capital M years of data. And then let me indicate with me tau the average value, the mean value of the data observed in the day tau, where tau is varying from 1 to 365. Okay, this is equal to 1 over m times the summation from I equal 1 to m of, okay, let me call the data x. So x x tau plus I minus 1 multiplied by 365. I think this is correct, because if we have I equal 1, then we have x tau. And then for I equal 2, we have tau plus 365. Yes, I think it is correct. Now, let me define the standard deviation of tau, which is equal to 1 divided by m minus 1 summation I equal 1 to m x tau plus I minus 1 365 minus tau, okay, squared. Okay, let me just check it 1 second. Okay, I think it is now correct. I just would like to bring to your attention that these are just the average value of the data observed in each day and the standard deviation of the data observed in each day. So basically, if you have capital N years of data, you have capital N data observed on the 1st of January, capital N data observed on the 2nd of January, and by referring to each day, 1st of January, 2nd of January, and I call the day with the symbol tau. You compute mean and standard deviation. And tau, of course, is varying between 1 and 365. Okay, now, if you understood these definitions, I can write down the analytical relationship for performing the deseasonalization. Okay, now I can write x, let me call d, because it means deseasonalized, of t, and let me introduce an additional index for clarity, because xt would suffice, sorry, I'm not sure I pronounced it correctly, it would be sufficient, xt, okay? But in order to be clearer, let me also put the index down here, which means that x is observed at time t, where t is varying from 1 minus equal t minus equal 365 times m. So x refers to time t increasing from 1 to 365 days in a year times the number of years. And refers to the day of the year tau. Tau is varying from 1 minus equal tau minus equal 365. So this is equal to, let me go on the new line. This is equal to x t tau minus me tau divided by standard deviation sigma tau. So be careful here, I introduced the double index also for x, which I didn't use here, okay? For the sake of clarity. I didn't use it here, but I introduced the double index here. So what I'm doing with this relationship, be careful, to each data point, I am subtracting the mean of the data observed in that day, and I am dividing by the standard deviation of the data observed in that day. So, if the data point x was observed on the 1st of January, I am subtracting the average of all the data observed on the 1st of January, and I am dividing by the standard deviation of all the data observed on the 1st of January. This is very trivial, so the mathematical definition may look complicated, but it's very trivial. And the resulting time series is no more seasonal, because, you know, if you refer to April, for instance, you have high flows, but then you subtract a mean that is high as well. So once that you subtracted the seasonal mean and you divide it by the seasonal standard deviation, you have the mean and the standard deviation that are constant. And in particular, the mean is equal to 0 along the year. You can make an experiment with R, and you could generate, for instance, a sinusoid, and then, which is of course seasonal, and then if you go and compute the average of the sinusoid at each day of the year, and you subtract this average from the sinusoid itself, you get a flat result, which is identically 0, which means that you remove the seasonality. Try that. It's very, very trivial, and again, this is something that analytically may look complicated, but it's very trivial. And this is a question that I may ask, because it's something that you can easily understand. And if you have some problems, please ask questions now or later, no problem.
I don't understand what is the XD.
XT?
Yes.
Yeah. It's the value, the data point. So let's suppose that you have daily flows of the 4 river. X is the river flow that you measured that day. And the number of total X is the number of days in the year times the number of years. So if you have 2 years of observations, you have 730 X. And basically from each of them, you subtract the average of the observation observed in the same day. It's still not clear. I'm not sure I am allowed, but I could explain, I make an attempt in Italian, okay? And then for the people who don't understand Italian, I just want a confirmation from you that you understood. Otherwise I repeat also in English. X è il numero sono le osservazioni, senza fare nessuna distinzione rispetto al giorno dell'anno. Sono le osservazioni, i numeri che lei ha raccolto. E se ha 2 anni di dati sono 730. Bene, da ogni X si toglie la media delle osservazioni osservate in quel giorno. È chiaro?
Però XD sarebbe, cioè, nel senso, quali sono le osservazioni? Non ho capito la differenza
Tra cosa?
XD